you were saying before, Professor, it's not really known why sometimes you get these big lobes and other times you don't.
Yep.
It seems obvious to me from what you've said. It seems like you get the big lobes when you reach a juncture in time where a lot of stuff is falling into your black hole.
That's almost certainly at least part of the story. And in fact, when we look at galaxies which tend to be a bit disturbed, you tend to find more of this kind of nuclear activity going on. And that makes sense because if one galaxy is interacted with another, that will disturb things from their orbits a bit, which makes things more likely to fall into the middle. So almost certainly that's part of the story. But what it is exactly that triggers some galaxies to do this and others not, we don't really know.
So these lobes basically are a really serious case of indigestion after a feeding frenzy.
And a big belch, yeah. And actually it turns out that we think it probably has a pretty big impact on the whole galaxy in the sense that, so one of the things when people are trying to study galaxy evolution and figure out why galaxies end up the way they are, one of the things people find is that you tend to end up with too many massive galaxies. Galaxies tend to keep growing and growing and growing. And you need something which switches off star formation. And the indications are that this kind of process where you throw a whole load of energy out from the middle of the galaxy through the rest of the galaxy can sometimes be enough to switch off star formation in the galaxy and stop the galaxy from growing. So it looks like this is one of the ways that actually galaxies interact with a black hole in the center of them and kind of sort of grow in harmony, that as the black hole grows it can actually switch off the star formation around it.
Professor, I'm not entirely clear from the graph, and I don't think I'm supposed to be entirely clear from the graph, whether most of this energy is coming from the magnetic field or the kinetic energy of the particles.
So it turns out that actually that point of minimum energy is where they're actually contributing roughly equally. You can see it just from the way the picture looks here, right? That actually one goes down and the other comes up, and the minimum happens round about where they're crossing over. So actually the minimum occurs pretty much where there's what's known as equipartition of energy, where there's as much energy stored in the magnetic field as there is in the relativistic particles.
But there's no reason to believe that is the case. It could be either side of that minimum. It could be high for either other reason.
It could be, but in that case things get even more ridiculous, right? In that actually we had a ridiculously large amount of energy down here at the minimum, but as you start going away from it, the energies get truly ludicrously big. And in fact, because the universe tends to be lazy and tries to do things in the minimum energy kind of way, there is actually an argument that says that probably the real universe is somewhere quite close to this minimum, which means there is roughly the same amount of energy in the magnetic fields and in the relativistic particles.
So that fixed luminosity that we can measure is unlikely to be caused by something truly ridiculous in terms of the speed of the particles or the magnetic field strength. It's more likely just...
It's likely. I mean, you need I guess you'd need to understand the physics at a level where we don't really understand it, of exactly what's going on in these jets. That this simple kind of argument tends to suggest that they're probably roughly equal to each other, but actually you'd have to understand the physics of the jet in great detail to actually get that balance exactly as to how much there was in the magnetic fields, how much in the charged particles.
Professor, I would have thought, I can't see how you would ever be able to measure the magnetic field from here. I would have thought astronomers would have a way of knowing how fast those particles are moving.
It's very hard because although you can sometimes see kind of blobs moving in these jets, that's not necessarily telling you how fast the individual particles are travelling, because it's very turbulent, it's very messy, so the individual particles could actually be travelling much faster than any individual blob within the jet is moving. There are actually ways to try and measure magnetic fields. So various subtle bits of atomic physics will let you try and measure magnetic fields. I'm not sure if there are actually direct measurements of the strength of the magnetic fields in these things, but in principle it could be measured.
I'm aware the Milky Way is not an elliptical galaxy. Does the Milky Way have lobes like this?
Probably not. I mean, there is radio emission coming from the centre of our galaxy. Potentially there could be emission coming from away from it, but really you usually see these kind of dramatic double lobe jet systems in elliptical galaxies, so the Milky Way probably wouldn't have one.
And also, I know orientation doesn't matter, but just because of the way that photo is chosen to be displayed, it creates the impression that these things are coming out the side. I assume these lobes come out of the poles?
They come out of so they're probably related, the direction they come out is related to the black hole, that you've probably got a black hole, stuff, kind of a disk of material spinning around it, falling into the black hole, and then material getting shot out of the poles. So it's really associated with the geometry of what's going on in the very centre of the galaxy. We do occasionally, you don't always see, I mean this one's clearly more or less sideways on. Turns out if you kind of were looking down the end of this thing, things get very dramatic, because then the particles that are being are charging almost straight towards you, and you get very strong relativistic effects which can make it very, very bright. So there are things called BL-lac objects, which are where we think that you're looking at this kind of system but really looking down, straight down the jet rather than looking at the jet sideways on. So this is the plot from one of Burbage's early 1950s papers on this, showing exactly the same thing that we were looking at before, where you've got the calculated magnetic field energy going up as the magnetic field varies, and the energy stored in the relativistic particles going down, and they cross over somewhere in the middle.
January the 1st.
January 1st, New Year's Day, and he's writing papers.
Absolutely.
First day of 1785. The figure we're really interested in, and you're quite familiar with this one, aren't you, Professor?
This is a very famous picture. In fact, I reproduced it in a book I wrote some years ago. So yes, it's a very, very famous picture of kind of the payoff from all this effort of measuring the numbers of stars in all directions is actually a map of the Milky Way.